So a typical physics question, when it comes to centripetal acceleration exerted by a large mass on a smaller mass, like a planet on a person, we have something like this where it says, what is the centripetal acceleration of a person standing at the equator? Now, a question like this makes a couple of assumptions. Remember that anything being pulled towards the center of a mass, in the case of a planet, it'd be pulling from the mass of the person to its core, right, or to the center. A lot of people associate the gravitational field strength of the surface of the Earth, or at the surface of the Earth, as negative 9.81 meters per second. You got to understand that that's an average acceleration. At the poles, so at the top, let's say over here, and over here, it tends to be about negative 9.83. It's the largest at the poles, okay? And that's because the person would have the longest time to accelerate, right, from the edge of the planet to the center. At the equator, because you're closest to the center, you have less traveling time. You could think about it as such. Even though it's not really what's happening, this is how we tend to conceptualize a problem like this. And so at the equator, you would have the lowest average of gravity, which is about negative 9.79 meters per second. Now, the acceleration, or the centripetal acceleration that the person would actually feel, would be the difference between the average, right, and anywhere else that they tend to be standing at the planet. However, because we're working with two extremes here, a question like this assumes that the person could have been at the pole and then gone to the equator. And so we're really looking at the most extreme portion. So imagine the person goes from the top over here to the equator. The change in centripetal acceleration between 9.83, because that's the value at the North Pole, and the value at the equator, is what's actually going to be felt by the person as they move around the Earth. Another couple things I want to kind of mention here is that there's generally two formulas to find the gravitational field strength, or the centripetal acceleration that the person is experiencing due to a planetary force pulling on them. The first one doesn't make mention of distances. It doesn't take any account of a change in distance from the person to the core, or to the center of mass. This formula over here, starred, takes into consideration the distance. So when you have something given like a radius, or in other cases they call it orbital distance, then you want to use this formula over here. And in our problem here, remember that for this formula, only the mass that is going to be really exhibiting the greatest influence between the two masses is going to be considered. And so this would be the mass of the Earth, and this is going to be the radial distance, or in some cases the orbital distance. And so I would plug in the constant, the Cavendish constant, with the mass of the Earth over here, the 5.98 times 10 to the 24, and then of course the distance that was given from the person to the center of the Earth, to which we would calculate, right, about a negative 9.799 meters per second value, second squared, or newtons per kilogram value at the equator. But remember, we're looking at what acceleration, or centripetal acceleration, the person is going to face, and that would be the change in acceleration. So if we start at the poles, which is negative 9.83 meters per second, and then we subtract it from negative 9.79, and we plug this in our calculator, we end up getting a value of roughly 0.031 meters per second, or newtons per kilogram. And so that would be the actual centripetal acceleration that is felt by the person as they move from wherever they are. In this case, we assume it's the poles to the equator. So remember that 9.81 meters per second squared, or newtons per kilogram, is really just an average centripetal acceleration that you feel when we consider the extremities at the poles and the lowest points at the equator.